Okay, so today we're going to be talking about asymptotics and disjoint sets, both of which are exceptionally interesting, so get excited. But before we talk about those, let's go over a few announcements. Midterm 1 is done. Good job. You guys are finished with that. Homework 1 is due today, and then homework 2 is due next week. And then, I'm sorry, but we've canceled some sections. Thankfully, not mine, since we're all here. And yeah. Okay, so we're going to start off by going over some content review. The plan for like the rest of section is we'll be going over asymptotics. And in asymptotics, I like to think about it as two parts. There's the asymptotics of iteration, like using loops and stuff, and there's asymptotics using recursion, like having multiple recursive calls. Okay? For this discussion, we're only going to be focusing on asymptotics of iteration. Next discussion, we'll be talking about asymptotics with recursion. And asymptotics is amazing. It's really, really cool. So next week will be very, very fun. Okay. The next thing is we'll also be talking about disjoint sets, okay? Just taking a quick poll, who has seen the disjoint set lecture, which was today? Can you guys like put a yes in the participants tab? Okay, nice. So some people haven't, that's totally fine. I'm gonna give you guys a brief rundown, maybe like 10 minutes on the disjoint sets. If you guys feel it is redundant, that's totally fine. You guys can zone me out, but it seems some people haven't, so I think it'll be helpful. Okay, so we'll do some disjoint set review, and then we'll do some problems on disjoint sets, and then we have one final challenge problem that combines disjoint sets and asymptotics. Exciting. Okay, let's get started. So what is asymptotics? Asymptotics is how we can describe the runtime of a function, okay? So when we think about runtime, there's three bounds that we like to use, okay? We have big O, we have big omega, and we have big theta. I'm going to try to describe these bounds in intuitive terms that might help with you guys for understanding, okay? We could think about big O as a bound that our function can never do worse than, okay? So what do I mean by a function can never do worse than? We could think about runtime as something that takes longer is bad. Something that's quicker is good, okay? So think about a big O bound as a bound on how bad our function can be, okay? Like some examples is if we have a list, let's say we have some list, and in the list, we return true if the number 4 exists and we return false otherwise, okay? This function, worst case, right, will take n time where n is the length of the list because we have to look through all the elements, right? So we could say big O of n. That's, if everything goes poorly, this is as long as the function will take, okay? So what is big omega? Big omega is the same idea, but it's a bound on how good our function can be, okay? So if we have some list and we're looking for the element 4, right? The best thing that can happen is if 4 is the first element and our function takes constant time, right? So think about big omega as a bound on how good our function can be. Big O is a bound on how bad it can be, okay? And then big theta is a cool occurrence when big O, the tightest big O bound is equal to the tightest omega bound. Then we have a big theta bound, okay? Big theta is saying that our function always takes the same amount of time, okay? That's what big theta is saying. And the reason is if big theta only happens when big O is equal to omega, that means that our worst case and our best case are the same, so we only have one case, right? Our function does the same thing every single time. A good example for this is if we want to sum up all the numbers in our array, let's say we have a function that sums all the numbers in an array, it'll take us n time worst case, it'll take us n time best case. This means our function always takes n time, so we can give it a theta bound of n. Okay, so I'm going to open the floor for questions on like these bounds. Nice. Okay, so let's keep going with the worksheet. Okay, so this problem is problem 5. This is later in the slides. I'm going to send a link to the slides again. So this problem is not on your exam prep worksheet. That's totally fine. Go to the slides at tinyurl.com/examprep06, and it should be problem 5 there. Okay? So these two problems are very fundamental in iterative asymptotics. Okay. So these are two like fundamental problems in asymptotics of while loops and for loops, okay? How I like to approach them is I want to count how many steps that we take each iteration of the for loop, okay? So what I'm going to do is I will create my loop. So this is the first time I enter, the second time, the third time, the fourth time, and so on, okay? So what I'm going to do is keep track of the number of steps we take in this for loop, okay? So for the first time we enter, when I is equal, we'll say i's values are here. Okay, we need to start at, okay, so when I is equal to 0, we do 0 work, right? When I is equal to 1, this print line gets printed 1 time, right? When I is equal to 2, we print this line out 2 times, right? We can think of this as the work that we're doing. When I is equal to 3, we execute this line 3 times, right? And so on. And what we can see is that every time we enter this for loop, right, for every I, we do I work, okay? I'll say that again because that's basically the crux of this problem. When for every I, we do I work. So the total amount of work that we do is going to be 1 plus 2 plus 3 plus 4 all the way up till n minus 1, right? Do you guys see that? Because we do 1 work the first time, 2 work, 3 work, 4 work, etc. Okay? So what does this summation equal? Okay? I can tell you guys what it equals, and you guys can just memorize that, and life would be amazing, and you do well in this course, but I'll quickly prove it to you. Okay? So let's say that we group these two terms together. What does that give us? Right?
N.
N. And then now let's say I group n minus 2 and 2 together. What does that give us?
N.
N. Okay, so we could see here that we have n over 2 terms that sum to n. Do you guys see that? Because all the way up from 1 to n over 2, there'll be a matching term that when you put them together, the sum is n. And if we have n over 2 of these terms, right, we could see this gives us roughly n squared over 2. Okay, it's not exact. Like, we don't really care about like exact formulas in asymptotics, but the gist is that this summation comes out to n squared, right? Once we get rid of the coefficients, because we don't care about coefficients in asymptotics, okay? So for the first problem, what we can say is that this function runs in theta of n squared. And the reason we can use a theta bound here, this is very important, is this function will take the same amount of time to run every time we call it. There is zero ambiguity, right? There's nothing different that can happen if I call it one time versus I call it the other time. Okay? So because of that, we can give it a theta bound. Okay? Okay, so we have a question. This is sent privately. Okay. So can I repeat how I got n over 2 times n? Okay, good question. So if we look at this sum here, we could see that if I take these two terms, they sum to n. If I take 2 and n minus 2, it sums to n. So we have n over 2 terms that sum to n. N over 2 times n gives us n squared, right? So this is like, I'm not accounting for like off by 1 things, it's just more intuition. Okay, perfect. So let's look at the next problem. Okay, I'm gonna get rid of this. Okay, so the next problem, I doesn't increase by 1, it increases by double, right? So what happens here is I will be 1, then 2, then 4, then 8, all the way up till n, okay? Each time we enter the for loop, we're still doing I work, right? Okay, so what we can see is that the sum of the total work that we're doing is simply going to be 1 plus 2 plus 4 plus 8 plus 16 all the way up till n, right? And this is like not accounting for like small like off by 1 things, which doesn't matter in the grand scheme of asymptotics, okay?
Quick question.
Oh,
Yeah, because I is 0, so then wouldn't it just infinitely loop?
Yeah.
oh,
Yeah, 'cause
okay. That's my bad. Okay,
Oh.
it would be an infinite loop. I meant to start I at 1. Okay, I apologize. That is a typo. Okay, good catch. Okay, so if you guys thought it was an infinite loop, that's my bad. I'll give you guys 30 seconds to try to think of what it'll currently be. Okay, we're back. I'm sorry about the typo. That is definitely my bad. Okay, but assuming that we start IF at 1, we will get this as the work that we're doing, okay? And what does this sequence equal, right? What is the final sum of this sequence? So when we think about asymptotics, there's 2 sequences we work with. The first one, I'm going to go back up here. I like to think about it as an arithmetic sequence, right? Where we increase by a number, right? It's like where we keep adding a number, okay? This one is more of like a geometric, okay? This is like not too much about math. I'm not a huge fan of math, right? We're just multiplying each time, right? Multiply by factor, okay? So if we look at any sequence that multiplies by some factor greater than 2, what we're going to realize is that the last term in that sequence dominates, okay? What do I mean by it dominates is, let's say that we only had this as our sum. Do you guys notice that 16 is greater than the sum of all of the previous terms, right? That's pretty cool. So what we can kind of say is that if we ever have this dominating sequence, the final asymptotics of this dominating sequence is simply the last term, okay? Because this term dominates all of the other ones, right? So what we can conclude is that the runtime of G will be theta of n, okay? And the reason for this, it's a dominating sequence. The last term dominates. What is the last term? N. This means it runs in theta of n, okay? Sorry again about the I equals 0. Does anyone have any questions?
So you mentioned we can say theta when there's no ambiguity. Do you think we'll go over an example where there is ambiguity? Okay.
Yeah. So we'll go over that example. That's happening later in this discussion. Don't worry. I got you. Okay. So any other questions? Okay. Question in the chat. Isn't this also a case where n over 2 terms equal n? Okay, so this sequence is a bit different than the previous one. Okay, the reason this one is different is we can't really pair terms like we did in the previous example. What's happening here is that this last term just kind of dominates all of the other ones. We know that n is going to be greater than the sum of all of the previous terms, in which case the runtime becomes, if we want to be exact, like around 2n, and we can get rid of the 2. Okay, so that's kind of how it works. And yeah. Okay, so I can also talk afterwards if it still doesn't click, but let's keep going. Okay, so the next thing we're going to be talking about is disjoint sets. This is a complete pivot from asymptotics. So I'm going to start off by doing a bit of a mini lecture. Okay, the problem, this is really, really cool, by the way. It's amazing. Anyways, the problem that we want to solve is we want to create some sort of data structure that will enable the following 2 functions, okay? Connect and is connected, right? What connect does, it takes in two numbers and it connects them together. What isConnected does, it returns true or false if two numbers are connected. Okay? I like to think about it as you're building a social media network where you have a ton of people and people can become friends, right? So you can befriend people and you can check if people are friends. Okay? That's kind of what's happening here. And if two people are friends, and if A and B are friends and B and C are friends, it means A and C are also friends. Okay? That's like this problem. We're creating this network. Okay, so let's look at a quick example of what I mean. Let's say that we execute these operations. Okay, we call connect 1, 2. What this is doing, it's saying 1 and 2, you guys are now friends. So I like to think about it as now 1 and 2 are part of this connected component. Okay, that's a really important term, so I'm going to write it down. Right, it's part of this connected component. Perfect. Okay, now what happens when we call connect on 2 and 0 is we're basically merging the connected component that 2 is part of with the connected component that 0 is part of. Okay, so 0 doesn't have any friends, so all we do is we add 0, 1, and 2 like this. Okay, and then if we do isConnected of 3 and 4, this will give us false because 3 and 4 are not friends. If I do isConnected of 0 and 1, that would give true because 0 and 1 are friends, right? Okay, so this is the problem we're trying to solve. And how we're going to solve it is we're going to keep creating solutions and making them better as we go on, okay? The first way of solving this problem, and all of these solutions have an underlying array implementation, okay? And we can assume that all of the members in our friend network are numbers, okay? So assuming that we have the number 0, 1, 2, 3, 4, we're going to create an array, okay? And the value of each element is going to be the leader of its group, okay? So what does that mean? Initially, this is called quick find, by the way. Initially, all of these numbers will just be set to themselves, okay? Because they're all part of their own groups. Then when I do connect of 1, 2, we're going to say 1 and 2, you guys are part of the same group, so your value here is going to be the same. Arbitrarily, I'm going to choose 2, okay? So now that we have 1 and 2 together, we know they're part of the same group because their value is the same, okay? The next thing that we do is we do connect of 2, 0. So what do? Is we set 0 to be 2, right? Another way that we could have done to solve this problem is we could have set 1 and 2 to be 0, okay? So what you guys can kind of see is that merging groups together takes a lot of time, right? Why does it take a lot of time? Well, if we're merging the 1, 2 group with the 0 group, we need to know all of the members of the 1, 2 group. What this means is we need to iterate through the entire array to see all of the values that are 2, right? We also need to iterate through the entire array to see all the values that are 0. So because of that, quick find is bad because connect is time consuming, right? Okay, so let us improve our implementation. The next implementation is called quick union, okay? Before, we thought of connected components as just like a group of numbers, right? We're going to build on that definition, and now we're going to say that a connected component is going to look like a tree, okay? So if we look at this 0, 1, 2 connected component, how we're going to visualize it is as a tree where I'm just going to choose 1 to be arbitrarily the top. It'll look like a tree like this, okay? Where we have one element, okay? This is the root, right? And then each other element is going to have one parent, okay? So you can see here that the parent of 2 is 1, right? So what we're going to do in order to describe this tree in the array is that each element is going to store the value of its parent, okay? So assuming that we have the trees of 1, 0, 2, right? This is one connected component, 3 and 4. What we can do is we know that 0's parent is 1, so we'll put a 1 here. We know that 2's parent is also 1, and we know that 1 is the root, okay? For now, I'm just going to say a root is -1, okay? So now we've described these connecting components, and this is what quick union does, okay? So the next question that probably arises is how do we know that two elements are connected, and how do we actually connect elements together, right? Our data structure, oh gosh. Our data structure is supposed to support these two operations, so how do they work in a quick union? That's a very good question, let's see. So if we want to connect 3 and 1, what we want to do, most likely, is say 3, you will now be a child of 1, right? So a connect operation, what it's doing, it looks for the root of the first number, then it finds the root of the second number, and it'll set the root of the first number to be a child of the root of the second. Okay? I'll say that again. If we want to connect 3 and 1, the first thing that we want to do is find the root of the 3 component and find the root of the 1 component. Okay? In this case, 3 is already the root and 1 is already the root. Then what we want to do is set the root of the 3 component to be a child of the root of the 1 component. Okay? So this is what quick union is doing. And how we signify that is here, 3 will now point to 1. Okay, because 3's parent is 1. Okay, so I've been going kind of fast. I apologize. Does anyone have any questions? Okay. I'm going to keep going. I want to make this kind of quick to get to the actual problems. So the problem with quick union is that when we combine two groups together, we don't take consideration the size of those connected components, okay? This is a problem because if we have a really big connected component, we connect it with, I don't know, a connecting component of size 1, we don't want this whole connected component to be a child of the smaller one, right? The smaller connected components should always be a child of the bigger ones whenever we connect connected components together, okay? To optimize for that, what we're going to do is beforehand, the root was storing meaningless information. -1 gives me nothing but telling me that I'm a root. So now the root will store the negative number of the size of its connected component, okay? So 1 will be -4 because its connected component is of size 4, right? 0, 1, 2, and 3 are the same, okay? Or 0, 2, and 3. And then 4 will be -1 because its connecting component is of size 1, okay? So that's what weighted quick unions do. They take in consideration the size, so when we connect connected components together, it's better, okay? And then this last topic is pretty confusing for a lot of students, so I'm going to go into it a bit more depth than the other things I talked about. It's this idea of path compression. Okay, I'll take the questions like when we get in the problems. So what is path compression? Let's say that we have some tree, okay? So a common operation that we do in weighted quick unions is we want to find the parent of a given element, okay? Like, let's say that we want to do connect 4 and 5, right? What we want to do first is find the parent of 4. So how we do that is we keep iterating up this tree until we get to the parent, okay? All path compression is a simple optimization. Is if we're already finding the parent of 4, what we're going to do is all of the elements on this path from 4 to 1, we will connect to 1, okay? So what this means is after we perform path compression, now 3 and 4 are both going to be children of 1. The reason this should make sense is if we're already going up to 1, it is much better for our data structure. The trees having a smaller height is better, right? So if we're already going up to 1, we can just store 4's parent, right? We're going to say 4's parent, you're going to be 1. 3's parent, you're going to be 1. Every other node on this path from 4 to 1, their parent will be the root, right? So what this does is it allows our trees to have a smaller height, and it improves in the runtime of operations. Okay? So I'm sorry if that went fast. I wanted to get to the questions, but I noticed some people missed on lecture, so this is needed. Okay. The first question we're going to do is question 1. Okay? And if you guys have questions, feel free to ask them now. If you guys don't have questions, get started on question 1. And all question 1 is saying is, we have a bunch of arrays, A, B, C, D, and F, right? These arrays have these elements. And it's asking which of these can be are possible weighted quick union arrays with path compression. Okay, so that's what the problem in the exam prep worksheet is saying. I'm going to say it once more, is we have a bunch of possible arrays, A, B, C, D, and F. We're going to look at each array and ask ourselves, is this a possible implementation of a weighted quick union with path compression? Okay, I'm going to build on top of that to say, is it a possible weighted quick union with path compression? You guys will also check if it's just a possible weighted quick union. Okay, and the last check will be if it's a quick union. Okay, so this is in addition to the exam prep worksheet I'm building on top of it. For each one of these arrays, you want to say whether it could be a quick union, whether it could be a weighted quick union, and whether it could be a weighted quick union with path compression. Okay? Okay, so that was intense. This is recorded, so you guys can watch all of that again. Don't worry. But let's get started with this problem and ask questions if you have any. Okay, good question. So the question is, why is path compression even helpful to begin with? Okay. I recommend if you guys trying this problem and you guys understand path compression, just mute me, but I'm going to respond now. So let's say that we have, okay, so if we have any type of tree, right? Let's say this is one tree that we have, right? And let's say that we're trying to merge it with, I don't know, this other tree, okay? What we're going to notice is merging them together will probably look something like this, right? And this is really bad because 10 is so far down from the top, right? And even if we had an actual binary tree here, 10 would still be really far from the top, right? So what path compression does to improve this is when we merge these connected components together, what we're really doing is we find the parents, right? That's the first thing we do. And then we set parent to be child of other, okay? So if we're going from 10 all the way up till 2, it's much more advantageous in the long run for us to say that 10, you will now be a child of 2, right? That makes sense because now the height of our tree is less. And we can not only do that for 4, but we can do that on all elements from 10 till 2, right? Okay, so hopefully that makes sense. I'm sorry. Okay, why is the weighted component? Okay, I might have had a typo on Jerry's question. I'm sorry about that, but okay. Okay, I'm gonna walk through them. So there's one small helpful trick that will prove beneficial for problems parts D, E, and F, and I'm sorry I didn't go over that, but let's get started. Okay, so the first one, what we can see is we have this thing right here, which looks a little suspicious because it is suspicious. What it's saying is that 0 is a child of 1, right? 1 is a child of 0. Yeah, 0 is a child of 1, 1 is a child of 2, right? 2 is a child of 3, and then 3 is a child of 0, right? So we have this cycle, and this is not a tree, okay? So because of that, we know it cannot be any one of all of these, right? Because in a weighted quick union, all of the connected components must be trees, and this is not a tree, right? Nice. Okay, let's look at, so we could say X for all. Okay, for the next one, for B, what we can notice, I think these 4 are the most exciting, so I'm just gonna only go over these 4. You guys can look at the solutions for the other 2, okay? So for B, let's quickly draw out how the tree will look. We have 0, okay? We have 9 as at the top, then we have 0, then we have 1, 2, 3, 4, right? And we also have 5, and then we have 6 and 7 as and 8. Okay, right? This is the tree. So looking at this tree, it looks pretty reasonable, right? The only problem with this tree is it should look like there's too many people down here, right? So this is a valid quick union, okay? This is a check on the quick union because this is a tree, right? Quick union basically only checks for if what's given is a tree. But in regards to a weighted quick union takes in the size of the connected components before merging them together, okay? What that means is in order to merge, like in order to get this tree structure, at some point, we probably had to merge this component and this component together, right? Do you guys see that? That we had to merge, like we probably would have to merge these 2 components together in order to get this bigger tree, right? If we directly connected 5 and 9, then 5 would look like this. So the only way to even have this possibility of this being a valid connected component is to, at one point, have these 2 connecting components and merging them together. But here we notice that this connecting component is larger, so a weighted quick union will set this component, right, this as the root, right? So what would actually happen if we merge these 2 connecting components together is that 9, right, and all of these ones, right, and 8, 7, 6 would be children of 0, okay? So this is not valid for a weighted quick union, and it is not valid for path compression because path compression is a weighted quick union with a simple optimization, okay? So let's go over C. What C is saying is we have basically a linked list. Do you guys see that? So we have this linked list structure of 1, 2, 3, 4, 5, right? All looking like this. And this isn't possible because there's a cool property of weighted quick unions. And the height of a weighted quick union is logarithmic to the number of elements in that tree, okay? So there's this property for every tree, the height of tree is log n, where n is the number of elements, okay? So because of that, we can't have this linked list structure, okay? So the last thing that we need to talk about is D. I'm not gonna go over E and F just for the sake of time, okay? So looking at D, D is, okay, so this one is valid, but not for these 2, because it is a tree, but it's not like the tree that we're looking for, okay? So looking at D, what we see is that 0 is the root. It has children, 1, 2, 3, 4, 5, and 6, it looks like. No, it has 0, 2, 3, 4, 5. And then 6, 7, 8, Okay, 6, 7, 8 are children, right, of 1, and then 8, yeah, okay, so then 6 and 8 are related, right? Okay, I slightly messed this up, my bad. Should be 5, 6, 7 here. And then 6 and 8. Okay, and 9 and 2. Okay, so I think this is the correct drawing. This is an actual weighted quick union, and the way that you guys would arrive to this conclusion is, let's just walk through some operations we can do to make this happen. Okay, I'm going to show you guys a step of execution that will prove that this is a possible weighted quick union that could arise. Let's say that we first connect 6 and 8 together, right? This will happen. Now let's connect 1 and 7 together. Now let's connect 1 and 6, right? You guys see that this is the structure? Because
just a disclaimer, you connected a 5 to 0.
Oh, okay, where does 5 go? Oh, 5 goes to 1. Oh, yes, yes. Okay, is this good now? Okay, perfect. Thank you, thank you. Okay, so let's keep going with this example. Then we see that this is our current state right now, what's in green. We can connect 5 and 1 together, and we get this, right? And notice that I'm doing path compression right now. I'm just choosing to not choose leaves, right? Path compression only optimizes for when we connect leaves that are like farther down the tree, right? So I'm doing path compression, but like there's nothing to path compress. Okay, now let's build this other side. What we can do is we can connect 2 and 9. We can connect, I don't know, 0 and 4. We connect 0 and 3. We could connect 0 and 2. And then finally, we can connect 1 and 0, right? And then we've created this tree. So this is a valid weighted quick union, and it's also a valid path compression. Okay, so does anyone have any questions?
I understand that it's a weighted quick union. What the reason it's a quick union with a path compression?
Yeah, good question. So let's quickly walk through all of these steps, and then we can try to prove to ourselves that we never do path compression, okay? So the quick reason why we never do path compression is that path compression is only really helpful if we have something that's like 2 down, right? Like if we ever have like a 0, 1, 2, and we have a 3, 4, right? When we combine, like when we find the parent of 2, we say that 2 actually points to 0 now, okay? That's the reason path compression is helpful, because if we find the parent of 2 in this case, we set it equal to 0, because the root of the 2 path is 0, okay? So let's see if we ever could do this optimization in the steps that I outlined before. We connect 6 and 8, nothing's happened. We connect 1 and 7, nothing happens, right? We connect 6 and 1. Do you see that like there's no path compression that can happen because 6 is already pointing to the root, right? If we were to connect 8 and 1 together, then we could do path compression. But I smartly chose to avoid path compression for the sake of this problem. Okay, then we can do 5 and 1, no path compression, 2, 9, right? There's no path compression that's happening because I'm choosing the proper elements to connect, right? Okay.
Thank you.
Yeah, you're welcome. Okay, any other questions on parts A, B, C, D? Okay, so I've created a fun disjoint set and asymptotics problem. I'm sorry, I misjudged how long these would take. So if you guys want, you guys can feel free to head out now. My feelings definitely won't be insulted. I know you guys have a lot of stuff to do, but if you guys want to learn and want to like try out new problems, definitely stay. Okay, so this is problem 7 in your slides, okay? So what it's saying, what are the answers for E and F? They're both false for weighted quick union and path compression because the height of the tree is too big. Yeah, and then they're true for quick unions. Okay, so if we look at a weighted quick union, we will be working with the asymptotics of stuff with weighted quick unions. Okay, very exciting stuff. Combining two fields to make something even more cool. Okay, so let's first go over the runtime of is connected and union in the worst case. Okay, I'll give you guys like 30 seconds, a minute, try to think about what is the runtime of these operations. Okay, so for the first problem, for 7a part 1, we know that it runs in big O of log n, as Patrick said. The reason for this is because every tree, right, has maximum height log n. Okay? There is a good proof that Hug does in lecture, but for now I'm just going to assume that it's true. Okay? So if every tree has maximum height of log n, it'll take us log n in like that's as bad as it can be. So a tight big O bound is big O of log n. Okay? And if we think about omega for part 1, there's a pretty good possibility that these, like the two numbers that we're connecting, aren't the leaves of some tree, right? Or they've never been connected before. So a lot of times is connected will take constant time, right? Like let's say that we have 1 and 2 and they've never been connected, right? It'll take constant time. Or let's say 1 and 2 are the roots of their respective subtrees, it'll take constant time, okay? So we can see here that that's the behavior for 1. And so the real question is, what is connect even doing? What connect does is we find the parents of the two elements that we're trying to connect, right? Then we perform a constant time operation of setting one parent to be the child of the other. So whenever we think about the asymptotics of these problems, I want to emphasize that we're looking for the operation that takes the most amount of time, right? So if we break down connect, right, it's two parts: find parents and connect. Okay, this is constant time, right, because it's just setting the array element. This is the crux of the runtime. Okay, so as we get deeper in this class, we'll learn more about these algorithms. We'll learn more about these like operations, and how we approach them is we find the parts of these operations that take the most amount of time, right? Okay, so how long does it take us to find the parents? Well, it's the same thing that we did in isConnected, which is big O of log n, and best case, or not best case, like the omega bound is 1. Okay, so does anyone have any questions?
So where, actually, I got confused by the log n here. Is that, that is log n, is that because we are dealing with a tree?
Yeah. Yes, so the reason for that is, let's say, like, what a big O usually bounds as bad as our function can be, okay? So if we have like n elements, it's possible that we have all of them in some big tree, right? Right, if they're all in some big tree, we know the height of a tree is going to be log n, okay? The proof for why it's log n can be seen in lecture. I can give it again, but I don't want to like spoil Hug. He explains it pretty well. So if a tree is of like maximum height log n, if I want to check if this is connected to that, I have to iterate all the way up to the top of that tree, right? So it takes me log n time to check if two things are connected. And is this for a binary tree? So for any type of tree that we use, like in weighted quick unions, the height will be log n. I haven't specified what the base is because we don't know what the base is, but best case, it could be like a better tree, right? It could just be like everyone's connected to the root. That's also a possibility. So, but just like in the worst case situation, the height will be log n, okay? Yeah. Okay, so now you guys might be wondering, this is an exam prep section, let's make it a bit more exciting. Okay, so this may seem like a bit confusing, but we will be analyzing the runtime of this function. Okay, what this function is doing is we have a bunch of elements. Let's say it's 1, 2, 3, all the way up till n. All this function is doing is it creates a list of all of the pairs of elements, okay? So our pairs, this is a cool problem. I hope you guys enjoy it. It'll be like 1, 2, maybe like 3, 7, right? It'll contain all pairs of these elements together, okay? Maybe like n1, okay? And then shuffle does, it just rearranges the ordering. So we have no idea in what ordering we're going to go through these pairs. Okay, then what we're going to do is for every single possible pair of elements, we're going to perform the operation connect. Okay, so the question I have is, what is the runtime of this function in big O? Okay, so let's go over this function. So all we're really doing, to recap, is we have all possible pairs of elements that's given to us in random order, and we just keep connecting people together, okay? So, and we want a big O bound on this function's runtime, right? So how do we approach this function? The first thing that we want to do is think, what can take the longest time, right? Like what will like cause our function to like spend as much time as possible? So one idea I have is, let's say that the first n operations like combine everything into a tree, right? So after the first n operations, we have a tree of all of the n elements, okay? And let's say the height of this tree is log n, right? That's a fair assumption because it's possible for that to occur, okay? So let's say that we have a tree of height log n, which was constructed after n operations. We know that how many pairs are there? There's about n squared pairs, right? So for the remaining n squared minus n pairs, right, how much time will it take to do connect of pair 0 and pair 1? Well, if they're always at the bottom of this tree, it could take log n time, right? So what that's saying is that we can break up this into two parts. We first create a tree of height log n, which takes us like maybe around n time. Then for the remaining n squared minus n time, we keep having these awful connect operations that take log n time, okay? So we see here that if we have n squared minus n operations, each taking log n time, what this simplifies to is n squared log n, right? So we can say a tight big O bound is big O of n squared log n, okay? And a quick explanation of why we cannot exceed this is that we know that there's n squared pairs. We know that the maximum runtime of a connect operation is also log n. So we can never do worse than this, right? So from the bat, we could have come to this bound. Using this example hopefully reinforces that. Okay. Any questions?
How do you get n squared minus n again?
Yeah, I was going to ask that.
Okay. So how many pairs are there? How many pairs are there?
N over half of n, right? Or
So think about like,
no?
there's n squared pairs. It's because if we have n elements, how many pairs are there that one's part of? N minus 1, right? Think about this. So if we have 1, 2, 3, 4, 5, 6, 7, 8, 9, how many pairs is 1 part of? N minus 1. How many pairs is 2 part of? N minus 2. How many pairs is 3 part of, right?
Can you explain what the pair function is doing? Because I don't even understand that.
Okay, I'm sorry. So if we have a list of elements like 1, 2, 3, 4, all the way up till n, it produces all possible pairs, okay? Think about it as like a nested for loop. Yeah, I'm sorry I didn't make that clear. Dang it, okay.
So we are, first of all, we are trying to pair one with the rest of the elements in that list, right? Then
Yeah.
we do that same thing on 2. Is that
Yeah.
what we're trying to do?
Yeah,
Oh,
pairs are just a huge list that contains a bunch of pairs, right? Contains all possible pairs. Does that make sense? Okay, and then we know the size of this list is n squared because we can use the same asymptotic argument I used in the beginning of this discussion for n squared, right? in order to create pairs, what I do is I'd say for I, this is Python, sorry. It'd be like for I in 1, this is not even Python, right? And it'll be like for j in I to n, it'd be like pairs add ij, right? Do you guys see like this is like a possible implementation of the pairs function? And then the runtime of the pair, or not even the runtime, but how many pairs are added is n squared, or asymptotically n squared.
Yeah, the demo makes sense. Thank you.
Nice. Okay. So, okay, let's keep going. Okay, so with the understanding of the previous part, we realize our function could be improved. Okay, how could it be improved? All we do now is add in this condition. Okay, what this condition is saying is once we have a connected component that consumes all of the n elements, we break out of this for loop. Okay, I'll say it again. Once we have a connected component of size n, okay, we exit. Okay, does that kind of make sense? Once everyone in our friend network is friends with each other, then like, hey, we're done. Okay, so now what's a big omega and big O bound after we added in this optimization? Okay, so we're going to quickly go over this solution. Okay, so in this question, we want a big omega, right? And recall that this is something our function cannot do better than, right? And we also want some big O bound, what our function cannot do worse than, okay? So let's do this one first, because it's kind of fun. So we want our function to run as fast as possible, okay? And imagine that you had the power to manipulate the pairs array to present it in the best ordering possible, okay? Because we're thinking about the best case, like we're thinking about like our function runs as fast as possible. What is this instance that produces it to run as fast as possible, right? We want to exit as quickly as possible, and we can only exit once our weighted quick union has everything connected together, okay? So let's look at an example. I'm gonna draw it out here. Let's say that we have 0, 1, 2, 3, 4, and 5, okay? Now, let's say we want to exit as quickly as possible. So let's say we first connect 0 and 1 together, okay? Now let's connect 1 and 2 together. Now let's connect 1 and 3 together, 1 and 4, and 1 and 5. You guys kind of see if I continue this pattern, I continue this strategy for all n, each connect operation that I'm doing here, right? Each connect that I'm doing is in constant time, right? If I'm choosing this strategy of saying one person, you are the root, everyone else connect to the root, right? This strategy takes n connect operations, each connect operation taking constant time. So we can never do better than n times constant time, or in other words, n time, right? So we can say omega of n. Okay? That's cool. So let's do big O. And for big O, I'm going to argue that our big O bound is going to be the exact same here as it was in the previous example. The reason is, let's say, it's actually n minus. Yeah, so when we think about asymptotics, good question. The question was like, is it actually n minus 1? So yes, like when I deal with asymptotics, I get rid of like all of these off by 1 things. So really good question. Okay, I'm going to argue that the big O bound is the exact same as the previous instance if all of the pairs that correspond to a specific number are pushed to the end. Okay, let's say that we have our pairs. Okay, and all the pairs that, I don't know, 0 is part of happen at the end. Okay, so before all the pairs, including 0, we still have like n minus 1 squared roughly pairs, right? So I can just say that we still have to do all of this work up till the point that we see the first 0. So we still have n squared log n work that we can do in this like big O case. Do you guys see that? That there is a possibility that we have one straggler that's all of the pairs involving that straggler are located at the end. So we still have a ton of wasted time until we get to the first pair consisting of 0, right? In which case, we have like n minus 1 squared, like roughly that many pairs, and each one could take us log n time. So big O of n squared log n, right? Because we get rid of like the off by 1 stuff, like -1 and small coefficients. Okay, does anyone have any questions? Also, I hope this is like cool, like when you guys see the solution at least. I know it may be like challenging in the moment, but like afterwards, if you guys like look back, you're like, oh wow, that's like such an interesting way of thinking and approaching problem solving. So with these strategies, you guys can like tackle them on your own. It's pretty fun. Okay, so we have one last problem. I'm sorry, I know you guys have sat here for so long. So for the sake of time, okay, big O of n. Question is big O of n constant or linear? Okay, O of 1 is constant, big O of n is linear. Yeah, I might have misspoke. Okay, so we have one last, this is a challenge problem, okay? I'm just gonna give you guys the problem, and then I'm just gonna like walk through the solution for the sake of time. This is really hard though. This is like insane. So let's say that we have a height increasing connection as when we merge two connected components together that are the same size, okay? What this is saying is when we have like, let's say we have two components, one of 1, 2, and the other of 3 and 4, when we connect these components together, I'm gonna call that a height increasing operation because the total height of the resulting tree is 1 more, right? So this is the idea called a height increasing connection is when we have two trees, we connect them together, and then the height of one of the trees goes up by 1, right? They're equal size and we connect them, okay? So imagine in the code, whenever we see a height increasing connection, we have like this tally that says tally plus plus if this connection is a height increasing connection, okay? So we're gonna do the exact same thing we did before, but now we wanna count how many height increasing connections they are in the worst case and in the best case, okay? Wow, that's tough, right? Okay, so I'm just gonna give you guys the solution. This is like pretty tricky, but let's kind of like walk through. And for this problem, this is like not entirely asymptotic because we want an exact number, okay? So let's assume that n is a power of 2. This will help us get an exact number, okay? Okay, let's first think about the worst case. The worst case is when we have as many height increasing operations as possible, right? Every time we perform connect, they're the same size, okay? This is really, really similar to stuff you'll see later in asymptotics, okay? So let's say we have 1, 2, 3, 4, 5, 6, 7, 8, okay? If we merge 1 and 2 together, that's a height increasing operation, right? Then we can merge 3 and 4. We merge 5 and 6, and we merge 7, 8. And at this level, we've done 4 height increasing connections, right? At the next level, if we continue this pattern of merging, right, we've done 2, right? And then the last level, we do 1, okay? So if you guys notice, the total number of height increasing connections we did in this worst case instance that I created is 1 plus 2 plus 4, which is equal to 7. How does that relate to the input n? Since n is equal to 8, notice that 7 is 1 less than 8, right? This is not a coincidence, right? This sum will always be 1 less than n if n is a power of 2, okay? So the most height increasing connections we can have is n minus 1. Okay, that's the worst case. Right? That's the most possible height increasing connections we have. Right? So if this doesn't make sense, you can watch it again. I've stayed here for so long, so I want to try to finish up. Okay, so if we think about the best case, we want to not have like any height increasing operations. Okay, the problem with that logic is we need at least one. Do you guys agree with me that we need at least one height increasing operation? The first two people we connect are size 1, so it'll take us one operation to connect them, right? So at minimum, we need 1. But I will show, using this example that I've created, that in the best case, there's only 1 that we need, right? To do that, to every other element, we will simply add it to the first group, right? Adding 3 to the group of 1, 2, not a height increasing connection. We add 4, add 5, add 6, add all the rest. No more height increasing connections but the first one. So you guys can see in the best case, in the situation that I've created, there is exactly 1. Okay. So this is like really challenging. Don't worry if it didn't like come to you guys at all. But I applaud you guys for staying in here for almost 2 hours. In the future, I'll make them shorter. I apologize. I just wrote this question up the other day and I thought it was really fun. So thank you guys for staying.
Thank you.